Hello everyone. Here in this lecture 2 of module 5, we are going to discuss about the direct sequence spread spectrum. Okay, we'll try to analyze what is the direct sequence spread spectrum, how will the methods we are going to do. So that will be then, and how we are making the modulation and how we are getting back the demodulation, and what is the effect of the interference and the probability of error. So this much we are going to see in this video. Now this is the what we are going to do in the direct sequence spread spectrum. So we can see it here that this is the PN sequence. Okay, this is the PN sequence. So this is what we are doing when we are giving it after the modulation. The first stage, what the modulation we getting, that is this one, that has been done with the PSK modulation. Okay, what is that? Plus 1 is what we are going to, that is given that it is plus 1 and a minus 1. So it is going to do this like this way. Okay, the plus 1 and the minus 1 here. We can have here also, we have to given here, that is also we call it as a NRZ format. It is not written into 0 any form, but it is crossing. So that's the thing. And what it is we are doing here, that is going to multiply. Okay, it is going to multiply here. You can see it here. Okay, so we have to take just one pulse at a time. See, I'm going to calculate on this basis. Please bear with my freehand drawing there. Okay, so just I'm taking a bit by bit. I'll get back to the direct sequence with the technical and the equations and all. Just I want to understand how the process it will be there. Okay. Okay, till here it will be more than enough. So now what is happening here, you can see. So this is the amplitude plus 1. Here also the amplitude is plus 1. 1 into 1 is 1. 1 into plus 1 into plus 1 is 1. Then here you see a minus 1. That's no, minus 1 into 1. It is getting minus 1. So what it is here actually going on the process is that the C of t, the PN sequence, has been multiplied with the data signal V of t. So what the output we are getting is the product of V of t into C of t, and which is also that following the same NRZ rule itself. Here 1 in plus 1 into plus 1, here plus 1, here minus 1 into plus 1, minus 1, plus 1 into minus 1, minus 1, minus 1 into minus 1, plus 1, plus 1 into minus 1, minus 1, minus 1 into minus 1, plus 1, plus 1 into plus 1, plus 1. So this is how we are going to do in the direct sequence spectrum. So it is getting spreaded over the spectrum there. Yes. So now this, if you know with the data here, now I'm going to implement this. First I need to know what is the C of t, then I need to know what is V of t, then after the product what it is going to do. Now the basic method of accomplishing the spreading is shown here as B, that is a V of t it was. So that is information bearing database signal is denoted as V of t, is expressed as V of t is equals to summation of n is equals to minus infinity to plus infinity, which is a of n into g of t into t minus n capital T b. This is equation 1. So what is this a of n is doing? A of n is telling whether it's plus 1 or minus 1. The amplitude level is going to tell, and which is here varying from minus infinity to plus infinity. The same as the summation. And g of t is the rectangular pulse of the duration, that is going to tell of each bit of how much duration. For example, if a t is the total length sequence of a data sequence, tb is the 1 bit duration of, okay, tb is the 1 bit duration. gt of t is nothing but the whole data sequence, rectangular pulse sequence, what we have got in the TB is the 1 bit. This signal has been multiplied by the signal from the PN sequence generator, which may be expressed as C of t. C of t is equal to summation of n is equals to minus infinity to plus infinity. That is into C of n. C of n is nothing, again representing the plus or minus 1 into P of t minus ntc. Again the same thing, P of t is nothing but the rectangular pulse of the duration, the tc. Tc is the 1 bit duration of which has to be multiplied with the tb, that's the bandwidth of that one. This one has been multiplied, as I said, the C of t has been multiplied by V of t, and we are getting the factor, the operation V of t into C of t serves to spread the bandwidth of the information varying. So it is getting that what is the narrow, it has been spreaded over there, which has been occupied by the PN generator sequence signal C of t. So it is trying to spread it. So spread spectrum, you can see it here. In this one, you can see it here. Okay, this is where you are seeing. This is the what we have got it in the signal, the data signal, that is the carrier signal, and this is the spread spectrum, and this is the spreaded spectrum. And remember, they are doing it in the frequency domain. That earlier what we showed it in the time domain. So you know the basics of this frequency domain. You have studied it in your DSP fifth semester. So after the multiplication, how this way I got this shape. Okay. Now, the product of the V of t into C of t amplitude modulates the carrier AC cos 2 pi FCT and generates the double-sided band surprise carrier DSBSC signal. So that we are again multiplying, and we are sending it to the carrier signal and sending it to the channel. Okay, that is AC into cos 2 pi C FCT has been multiplied with the V of t into C of t. What we have generated the sequence, and we have send it there. Okay. Since V of t into C of t is equals to plus or 1 minus of any time t, the equation 3 can be expressed as, so I am removing this plus 1 or minus 1. Okay, V of t of C of t, I can remove it. So which is telling that U of t is equals to AC cos 2 pi FCT plus theta of t. Okay, so if theta of t is equals to 0, that is V of t into C of t is 1. If theta of t is equals to pi, that is when Vt into C of t is equals to minus 1. So what is this? This is nothing but the rules of the PSK. So direct sequence spectrum is going to implement the PSK rule, and therefore the transmitter signal is a binary PSK signal. So rectangular pulse P of t used to represent the PN chip is called the chip. What we have got the P of t, which are used to represent P of sequence, is called as the chip. And the time duration of the pulse PT, is called as a chip interval TC. The reciprocal of a TC is called chip rate 1 by TC. The ratio of the bit interval TB to the chip interval TC is selected to be an integer. Okay, the TB by TC, that we call it as the LC. What is LC here? The LC is nothing but the number of chips of the PN code sequence per symbol information bit. Also, LC represents the number of possible 180-degree phase transition in the transmitted signal during the bit interval TP. So it is trying to tell how many number of the 180 degrees. So that is what we call the bit transition, whether it's from 1 to 0, 0 to 1, like that. What is the transition is going to understand by the value LC. So after the modulation, now we are going to see the demodulation on the direct sequence spectrum. So this is what we are getting it from the after the channel noise, what is that interference we say here. The concept of noise we are using here is interference. So after that, again it has been multiplied with the C of t, and we are removing that C of t component, only the V of t will be there. So again we are removing that whatever the signals, and just getting the signal which has been sampled over the TB, that the duration of 1 bit, and that we are given to the sampler of the time sequence. We are going to check with that clock signal with reference that for some particular duration of 1 bandwidth will be checked with the sampler, and then we have given it back to the decoder. This is how we are demodulating or a demodulation of the direct spread spectrum. So that is the thing. The received signal is first multiplied with the waveform C of t generated by the PN code sequence generator at the receiver, which is synchronized to the PN code in the received signal. This operation is called as a despreading. As what we are done is the spreading in the transmitter, that we are removing it back as a despreading. Thus we have B of t is equals to R of t into C of t. So that is when we are getting a received signal, R of t is multiplied with the C of t. So what is happening? AC of Vt into cos 2 pi fct, this is into ct. This is what we are got from the last thing, that what we are sending from the transmitter, and this is we are multiplying with the C of t. So C of t and C of t is become 1 is equals to 1 for all t. That is what we say, that when we multiply with those things, we'll get nullify and it will become 1. Okay, so what will happen here? B of t is equals to AC into V of t into cos 2 pi fct. So this resulting signal AC into Vt into cos 2 pi fct occupies a bandwidth of R Hz, which is the bandwidth of the information bearing signal. This is the actual information bearing signal, and that's the demodulator for despreading is simply the conventional cross correlator or a match filter. So cross correlator is used for the coherent detection, and the match filter is usually used for non-coherent detection, as we have studied in the ASK and PSK. Okay, so this was without the consideration of the interference. Now if you are considering the narrow band interference, so what will be the case? Suppose the received signal is R of t, as we are doing AC V of t into C of t into cos 2 pi fct plus I of t. This is the interference signal which I am going to think. If here interference was there, what will be the role of it, or how it is making the operation and how it is affecting the information. Okay, the despreading operation at the receiver yields through B of t is equals to R of t into C of t. AC V of t into C of t cos 2 pi fct plus I of t into C of t. Okay, AC V of t into C square of t plus cos 2 pi fct plus I of t into C of t. So as we know, this is the only the signal, and this is what the interference signal which has been multiplied C. So here we can see the effect of the multiplying the interference signal with the C of t is to spread the bandwidth of I of t to W Hertz. So this is how it is making it to spread it over the bandwidth. For example, now considering the sinusoidal interfering signal, I of t is equals to AI cos 2 pi Fi of t, where Fi is a frequency within the bandwidth of the transmitted signal. Okay, where I of t into C of t results in a wideband interference with the power spectral density I naught is equals to Pi divided by W, where Pi is equals to AI square divided by 2. That is what we used to study, remember, in the third module. That is the thing, is the average power of the interference. So we have the strength of the, what is the signal, the amplitude strength, or we call the what is the amplitude, it's a value there. Since the desired signal is demodulated by a match filter that has a bandwidth of R, the total power in the interference at the output of the demodulator is I naught into RB, where it is equals to Pi by RB, Pi into RB divided by W. Okay, so I naught is equals to, we are replacing by Pi by W, that is equals to, we are making it to W by RB, Pi divided by W by RB. What is this W by RB? Is nothing but TV by TC, that we also call as the processing gain, and we are representing it with respect to LC, remember? So that is what we are representing here. So Pi by LC. So this, the power in the interfering signal is reduced by an amount equal to the bandwidth expansion for factor W by R. So what is this W by R? Is the processing gain. So R is the bandwidth of the information bearing signal, and W is the bandwidth of the PN sequence. So what is that? The ratio of the bandwidth of the PN sequence to the bandwidth of the information bearing signal. We can say it as the processing gain. So this is what I explained it here. So we need to know to what ratio it is going to tell. If it is the bandwidth is more and R is less, so that time the gain is more. If W is less, R is more, so that time it's not a gain, that time it is a loss there. We cannot spread it. So that is what we want to say. And processing gain use the net effect in the reducing the interference power. So what is there. For example, if W by R is equals to TB by TC, so this is the bit rate divided by the carrier, what we are providing the carrier. If it is carrier signal is and to the TB is very good, we can make it the interference enter in this signal, we can be reduced. Okay, what is the probability of error? We have to think on it. The probability error for the direct sequence spread spectrum system with a binary PSK modulation is easily obtained from the SNR at the detector. That is SNR D is equals to EB by I naught. The probability of error for the sinusoidal interference is P is equals to Q into square root of 2 EB by I naught, where I naught is the power spectral density of an equivalent broadband interference. So this is what the thing. We don't have any derivation for that. Just we need to recite the or memorize the formulas here, probability of error. Okay, this is how we think, and this is similar as what we have done. So we will not derive here. The said probability of error, what is that? So that we have achieved it with respect to the SNRD, so which is nothing but the PSK modulation only, the same as the PSK modulation what we have done in the model 3 itself. So something we have difference with the interference I naught, that's it. Instead of N naught we are saying it as I naught. Okay, and that's why additive white Gaussian noise, it might be anything, but it says for something as the interference, we are considering as an interference, that's it. Now what is this interference margin? How it can be done? If we are expressing EB by I naught in a Q function as a EB by I naught is equals to EB is equals to PS into TB divided by PI by W is equals to PS by R. 1 by TB is equals to R. PI is equals to by W. The same thing I am going to present it. So now I am rearranging this thing, PI by PS and W by R, the processing gain, and this is the jamming margin, the interference power and the source power, whatever what we are utilizing here. Okay, W by R is nothing but processing gain as we have described it earlier. So if we are implementing this, the what we call it as the logarithm. So 10 log of, if we take it like this way, 10 log of EB by I naught is equals to 10 log of W by R minus 10 log of PI by PS it will be, but I'm rearranging directly. So 10 log of PI by PS is equals to 10 log of W by R minus 10 log of EB by I naught. So if I take it, so I will represent here PI by PS into dB with respect to equal to W by R into dB, that is with respect to dB, minus EB by I naught with respect to dB. So this is how we represent the interference margin, and this PI by PS dB is called the interference angle. So this is the factor. Need not worry too much of how we got and what is the factor. Just you need to recite formula. That's more than enough. Okay. In short, why this is we are done here, we need to think here. Okay, in short I will explain here. If this is the bandwidth what you are sending, okay, if you have the bandwidth what we are sending and this is the signal I am actually sending, so what is the this is a chance that the other noise is getting charged here. Okay, so remember, in that way this noise has to be avoided. So what we are doing, we are enlarging this thing, we are enlarging such a way that any other thing which has to be not be utilized. If there is space for anything to enter, so that you definitely will unwanted things might enter there. So we are trying in such a way, that anything unwanted signals to be avoided. For what that we are doing here, we are just sorry, what we are doing here, just if you wanted to send this message signal in this bandwidth, we are spreading over this one. Okay, we are spreading over this one. So if a noise want to enter also, so there's a minimum interference over this signal because there is no space left so that it can add into it. So it has to be utilized over the spectrum. We cannot design any kind of a 100% designs there, remember. So what we are doing here, we are covering off all those things. So this is depending here the narrow band and a broad band, you know it in there. Okay, the space utilization is more. The very good example is the broadband is a the what we are getting the broadband connections from the BSNL, etc., etc. Some M companies are there, so that all we can get. Narrowband is about like this, the bandwidth will be small. So if we usually what we do in the narrowband, we can make some kind of interference signal relay. So that all concepts will come. So you need not worry on those things. Just think that why the noise will occur and why we are using the spectrum. That's the thing concept. Okay. Thank you.